How y'all doing? It is Wednesday. It seems we have mixed reactions to Wednesday.
It's just the weather for me.
Oh,
It's
yeah?
giving me very like sleep vibes.
Yeah, gray skies just kind of, they make me sleepy and they make everything.
Yeah, exactly.
I suppose it doesn't help that I work in a gray building.
And in the basement.
Yes, the basement of a gray building, barely any windows. That said, if we tried to open some, we'd just get dirt.
I have a question.
Yes.
So you posted test one practice problems. Is there like an answer?
There will be. I plan on doing that today. But to those who haven't noticed yet, which is okay. Too many tabs open. I have too many tabs open. We're going to look at Brightspace real quick so I can point out to you where the practice test is. So, plan for today is to close out chapter 5, and that means we'll spend Friday reviewing everything we need for test 1. To show you the available materials for that review though, within the Brightspace page for this course, there is a section for each chapter, and within the test 1 tab, if you click on the tab itself, you'll have a list of everything we've talked about this semester between lecture and lab. And lower down in the tab, there's a bunch of older versions here that you can't see. What you can see is the practice test, which is a series of questions that if you can look at these and do them, you will be ready for the test. I'll be uploading an answer key for them, ideally today. Yes?
Will the test questions next week be similar to these, or will there be a question on there that we're like, it wasn't on the study guide?
Well, the questions will not be identical, but they will be similar. So the same concepts, and you should be able to do the same types of things that you see here, but they won't be identical. But like, say for example, we have a question here that references normal force and friction on an incline. So normal force, friction, inclines. Also normal force, friction, and tension here. Here we have tension and trigonometry. So those are two things that you need to be familiar with. Here we have projectile motion. The exact specifics of what the launch speed and angle are might be different, but projectile motion. So the concepts you need and the types of math you need to use are all here, even if the specifics change. To answer the question? Okay. Additionally, you should also use homework chapter 1 through 5 and quiz chapter 1 through 5 to review and study for the test. Again, answer key for this will be up, I plan for today, and on Friday we will talk about everything from the past month and a half, talk about how it all comes together for the test, and answer any questions that you guys have. How do you guys feel? I'll also point out again, doing this is completely optional, it's just a study aid. Anything else on your minds right now? Yes.
So for like the homework and stuff online, that's due at midterms, or?
It is recommended that you do them before midterms, specifically chapter 1 through 5.
Mm-hmm.
The way that the midterm score works for this class is that the first test is not the midterm. The midterm score is your current class average as of Friday the 13th. And your average is comprised of your test, your lab scores, your homework, and your quizzes. So if you don't do the homeworks and quizzes, that will affect the midterm score, but if I'm being honest, the midterm scores around here are basically just pass, fail. Like, it doesn't even give me letter grades, it's just satisfactory or D or F, unfortunately. So if you aren't doing the homeworks and quizzes, the midterm score will reflect that, but if you haven't done them and want to know, like, it's all right, finding my words, it's early. Also, question, sorry.
Oh, this is ask what percent is the homework worth?
Homework is 10%, and quizzes are 5%. So if you don't do them at all, that's 15% of the average, which again isn't a big deal. If you do well on the test and you've been coming to lab, you'd still have a B average if you just ignored those completely. I wouldn't recommend ignoring them, but you can ignore them completely and your midterm score will be fine. Like, the test is the big thing before midterm scores. Yes?
How do we know our lab scores?
The general rule is, as long as you're coming to lab and doing the activities and showing me your work and I can check it off before you go, your lab average should be an A. I grade the labs as you turn them into me, and the only real issue would be if you put it on my desk and take off before I look at it and let you know how you did. Cause
Yeah, because we have
Oh,
Edwards,
right.
and he just gives a check mark and that's it.
well, I keep forgetting this semester.
Yeah.
Someone help me with that. If he gives you the check mark, then it is satisfactory and you get EA for that week. Does that answer the question?
Yeah.
Okay. Yes.
If you wanna take the test on a different day, you need to just like talk to you, cause that Edwards.
You do not need to, like, you can take the test on a different day, and I'll point out again, lab sections are Monday, Tuesday, Wednesday, and Friday. Thursday does not exist. Thursday is a myth. You can attend any one of those to take your test. And unlike lab, where there's only so many chairs in the room, and I need to make sure that there's, a good number of chairs per people. For the test, that's less important. You can just show up to any of the days to take the test. So again, those are Monday, Tuesday, Wednesday, Friday. There is no Thursday lab. So if you come here expecting to take your test on Thursday, you'll be disappointed. Yeah.
So once you take your test, let's say you take your test Monday, you don't have to come to class for that week, or you do?
Correct, because the bulk of lecture next week is going to be test review, helping people who do come in like with their homework and test review questions. If people show up and don't ask questions, I'll start talking about something. So if you do come next week to class, I recommend you bring questions or bring things to distract me with. And I'll watch Superman lately, ask me something about that. How does he fly? I could ramble about that. Yes?
For the quizzes, do we get multiple, is it taking points off when we submit over and over, or?
It should not be. If it is, then there's still.
Yeah, I just can't see the score, so I don't know. I didn't think it was, but
That should have been updated.
I haven't checked in 5 days.
Okay.
Yeah.
Okay, so as of this week, the settings should show you your score after you submit it, and then you know whether or not you want to retake it or not. And it shouldn't take off points for repeated attempts. So that should all be updated. If it is not, please continue to let me know, and I will continue making sure it is.
Also, I was just gonna say that last question on chapter 1 and 2, I submitted exactly what you said and it still didn't work.
The quiz or the homework?
It's the homework. I mean, it's like 1 point, so it doesn't matter, but I just
I don't know, because I didn't put it in it. Which number?
Can you email me about that? So I've
It's
got
the
it
very
written.
last one.
Can you email me about that so I have it written down and check over?
Yeah, yeah.
Thank you, sorry.
It's okay.
Okay. Anything else on your minds right now?
available later today?
Yes. Now on Wednesday I have lab, so on Wednesday and also on Friday, my office hours are 12:30 to 1:30, and then after lab till 5. So once lab starts, you can look for me in my office or the lab room. And now that I have moved offices, I will post this information on the board next to my new office door. My new office is 109 at the very end, 109E at the very end of the hallway. Very end on the left, going that way. Anything else on your minds right now? All right. Got a couple things I want to talk about before we are done with chapter 5. On Monday, we talked about different forms of energy, namely kinetic and gravitational potential. I got one more type of energy to add to that list. To make sure everything about it is in your notes, this is elastic potential energy. This is a form of energy that is stored within an elastic object's ability to stretch. To give you a couple more vocab words, in physics, something is considered elastic if it is able to deform and then by itself return to its original shape. And definition of deform is just change its shape somehow. Loads of objects can deform. You can take a hammer and hit a rock and it will change its shape, likely by denting or breaking into pieces, but rocks don't tend to go back to normal after the fact, whereas elastic objects deform and then go back to normal after swinging around a few times. So springs, rubber bands, basketballs, they all deform but then return to their original shape. And whilst they are deformed, there is energy stored in the stretch of the object. You've probably noticed, possibly involving rubber band wars with any number of family members, that when you stretch an elastic object and then you release it, a bunch of energy gets released along with it. I can twang this spring and either launch possibly it forwards or launch some projectile affixed to it forwards. If you've ever done that with a rubber band or something like that, the way that works is, I'm going to try to jury rig a slingshot real fast. When I stretch, again, deform the spring, there is now energy stored inside of it, and I know that fact because when I release the spring, that energy is also released into the kinetic form. Thank you. And this happens anytime an elastic object stretches and then snaps back to normal. This includes springs, rubber bands, but also like basketballs and things like that. Because the second a basketball hits the ground, this marker is dying. Can't see that. Ooh, nice. It's hard to notice unless you're using slow motion camera, but the second the ball hits the ground, it does actually squash slightly. This is a bit of an exaggeration, but it does in that moment kind of pancake. And what happens is, an object stores EPE, elastic potential energy, if it is elastic and if it deforms some distance. This should actually say delta X, I apologize. And that delta X is the change in size of the object. So if this thing squashes by like 5 centimeters, 5 centimeters would go right there, and then there'd be a certain amount of energy that is stored inside the ball in this moment. And you know the energy stored because in the split second it hits the ground and pancakes, it's not moving, right? If you pause time right then on the floor, the ball's instantaneous velocity is 0. And then a second later, after it unpancakes, the energy is no longer elastic, it turns back into kinetic, and the ball bounces off of the floor. So it has its kinetic energy back after being temporarily stored for a second. How does it sound so far? Okay. So within this formula, delta x, it says delta x on your formula sheet. I forgot to change it today. Delta x squared is the change in size of the object. It's not the final size, it's the change in size. If I was doing this formula for this spring, if the spring is normally 1 meter long and I stretch it to 2 meters long, what is its change in size? If it goes from 1 to 2. 1, very good. You do not plug in the final length, you plug in the change in length. The other thing is the spring constant of the object. And spring constant tells you how tough it is to deform any given object. It's a constant that is measured in newtons over meters. It tells you how much force is needed to deform an object by a certain distance. If this spring had a spring constant of 10 newtons per meter, it would take 10 newtons of force to make it 1 meter longer. If the spring constant was 5 newtons per meter, it would take 5 newtons of force to make it 1 meter longer. So the bigger the spring constant, the harder it is to deform something. That'd be like a spring constant of like 1,000 newtons per meter would be a very stiff spring, like the shocks in your car. And there's a separate formula that can help you determine spring constant. Force exerted on the spring equals spring constant times its deformation, which can be rearranged to say K equals F over delta X, because again, it is the force per change in length. And so the stiffer the spring, the more energy that you store in its ability to compress or extend. Questions so far? All right. Now this is a new form of energy, meaning it can compress, or it can convert into other forms of energy that we've already talked about. So we'll do one more example that adds this type into the mix. We're going to push a block across a frictionless surface. So the initial stage here is going to look something like this. Exerting a force on an object for a certain distance along the table, pushing it out of our hands, doing work to give it energy. So we're pushing a 1.56 kilogram block along the table. We're exerting a 10 Newton force on it for 2 meters horizontally. No friction is opposing us, which is nice. After we push it that distance, we will release it. It will slide across the table all by itself before colliding with a spring that is affixed to the wall. This is just something that a lot of physicists use as an example. You know, you don't tend to encounter springs all that much in nature, but this is a way that we can have a spring in the example. We're going to basically be chucking this brick at a spring, throwing it across the table at a spring. Now, when you throw something at a spring, what do you expect the spring to do on impact?
Compress.
It's going to compress. As it compresses, what's going to happen to the thing we threw at it?
Bounce back.
Slow down. First, it'll slow down until eventually it comes to a complete stop and the spring is fully compressed. Then it's going to bounce back. And so this process is meant to show the transformation of kinetic energy to elastic potential energy back to kinetic energy. So this is our before state, where we have KE forwards and no EPE. Our after state, the spring will be compressed, so some delta X, and the box will have come to a complete stop. So before we have KE, after we have EPE, and then eventually we'll have KE again. I might be reading too much into your facial expressions. How does the basic setup of this scenario sound? Question?
Why wouldn't the delta X be the 2 meters across?
So that is the distance we are pushing the brick, which doesn't directly affect the spring. That's just kind of the wind-up period as we're throwing the box forward. Down here, it says the spring compresses, the spring is compressed by 15 centimeters. So this is the spring's delta X upon being compressed by the box. What that 2 meters is for. Where are all my markers going? What that 2 meters is for is for finding out how much work we do on the box. We're going to push the box with a force of 10 newtons for 2 meters, so we do 20 joules of work on the box. And that's the energy we are chucking it with. That's the energy we are giving it as we throw it forwards. So that's the first question written up there. We're doing work on the box, 10 Newton force applied for 2 meters of displacement. We're gonna do 20 joules of work. We're gonna give it 20 joules of kinetic energy. Questions, opinions, concerns? Yes.
Does that mean that joules is equal to newtons times V?
Yes. 1 joule is the energy required to exert a 1 Newton force for a displacement of 1 meter, assuming no friction. Now, as this relates to springs, we're doing work on the box, we're giving the box 20 joules of kinetic energy. That means that this box is going to bring 20 joules of kinetic energy into the system, and that kinetic energy is eventually going to become EPE in the spring. Total energy initial equals total energy final. We've got our before state here and our after state here. Kinetic energy initial plus EPE initial equals KE final plus EPE final. Initially, before the box collides with the spring, how much kinetic energy does it have? Yes.
So you said the 20 joules is kinetic energy.
Correct.
Why didn't we use the formula?
The formula for kinetic energy, we didn't know the box's velocity yet. We could find it, There's multiple ways we could find this information. So we could do this. And in fact, it'd be worth me showing you that to prove that this method works. To use this formula for kinetic energy, we need to know the box's velocity. To know its velocity, we need to know what speed it accelerated to. So 10 equals 1.56 times A. A will equal 10 over 1.56. So its acceleration is
6.4.
Say it again, sorry.
6.4.
Thank you. So that is the box's acceleration. It is accelerating over a distance of 2 meters. So bf squared equals the initial squared plus 2a delta x. Bf will be the square root of 0 squared plus 2, 6.4 times another 2. So after this work, the box should have a final velocity of 5.06 meters per second. We then use that in the kinetic energy formula. Square root 2. We get 19.97 joules, which is just shy of 20.
So when do we need to use the kinetic energy versus when we just use work as kinetic energy?
It kind of depends on what information you're given. I showed the work method because I mentioned the force exerted times the displacement of the object. And so I wrote the question. I knew that that would tell me work done. And in this specific case, the work we're doing is giving the box kinetic energy. If you'd instead just been told the speed the box is sliding across the table, then the quicker option would have just been the kinetic energy formula. Yes?
So does work equal the kinetic energy because it's frictionless?
Correct.
So if it weren't frictionless, we would not consider it.
Correct. In a frictionless environment, when you do work on something, it will gain that amount of energy. Specifically in this case, it is gaining it within the kinetic state, since the goal is to push it and make it move. Questions? Okay. My next question. Box is going to approach the spring is going to compress a certain distance, and we need to figure out what that box is, what the spring constant is, such that it is able to absorb 20 joules of energy and only compress by 15 centimeters. So I'm going to use this to, again, demonstrate the energy transformation. In our initial state, we've got KE and no EPE because the spring is in its original configuration. It hasn't deformed yet. So there's no delta X for the spring yet. So on the initial side, box has 20 joules of kinetic energy, and the spring doesn't have any EPE yet. Afterwards, we're pausing time right as the box stops and the spring is fully compressed. In this moment, how much KE does the box have left? 0, because it's not moving. And in this moment, that means all of the initial energy will have transformed into stored EPE. So 1/2 times our unknown spring constant times the spring's compression squared. So by knowing how much energy it absorbed, we can figure out what its spring constant must be in order for it to only have compressed by that distance. So 20 equals 1/2 K, and 0.15 squared is going to be a tiny number.
0.0225.
Thank you.
Okay.
And K then, divide by 0.5, divide by 0.0225. This particular spring has a spring constant of 1,777.7 repeating, just rounded to 0.8, newtons per meter. So it would take 1,777 newtons applied to this spring to make it 1 meter longer, assuming it doesn't break first. So, frankly, that's a very tough spring. I don't know if that's exactly what car shocks are rated at, but I'd say it's not far off. So that is the spring constant of this particular spring. I'd say this one's like 5 newtons per meter, just again, comparison's sake. And the interesting thing about spring constant, it tells you how much force is needed to stretch the spring a certain distance. And likewise, interesting thing about springs, because of Newton's third law, when you exert a force on it, it exerts a force back. So what we can do with that spring constant is we can also figure out the force that that spring is exerting back on the box. So this is the other formula with K in it from that previous slide. Spring constant times the spring's current deformation will tell you the spring force. This number is not only the force the spring is currently exerting, it's also the force that was required to get it compressed to that length. So about 270 newtons. Yes?
When you originally gave us the formula, you had K as negative K delta X?
Oh, yes. That is simply because spring force points in the opposite direction as the deformation. If I compress the spring inwards, it pushes outwards.
Right, but you want
Apologies.
our answers to be positive.
Good point. So if the deformation is positive, spring force would be negative. So the spring compresses in the rightward direction, the spring's gonna push back in the leftward direction. Thank you. And this is why the spring is going to push back on the box and launch it again. If the spring is compressed, not only does it have energy stored in it, it is actively exerting force back out. It can compress, but it doesn't want to. It wants to return to its normal length, so it will literally fight you to return to its original shape. All springs will do this. For me to stretch this one, I not only have to pull on it to get it extended, I have to physically keep exerting that force to keep it at this length, because it is likewise pulling back in on my hands, right? If you've ever done that with done this with a rubber band, it takes force to keep it like this. because it is exerting force back. It wants to go back to normal. So this is the force it will use to try to push itself back to normal, push against whatever is holding it in that position. How you guys feel? Now, springs are weird, admittedly. There's one more thing I want to talk about with you guys. One additional concept to add at the very end of chapter 5. I want to introduce it today, hopefully do a little bit of practice with it, and then on Friday we'll review everything, answer any questions you have, and I'll make sure everything makes sense before we move it to test territory. I'm going to show you this today just so that you've seen it and process it sooner. It's the last new piece of information for chapter 5. So we'll review springs on Friday, and we will also review this along with it. This is one last new variable before the test. And this is the physics notion of power. The thing about work, the physics calculation of work, it tells you how much energy something takes, but it does not tell you how quickly a task is performed. The work formula by itself, still seen here, work equals force times displacement, does not in any way tell you the speed at which a task is performed. The problem with this is, say I am currently trying to pull something across a field. I'm going to exert a force and try to pull something across the length of a football field, for example. And a tractor can be doing the same thing at the same time. That tractor can exert a force on an object, pull it the same distance, and as long as we are exerting the same force on two different objects for the same length of the field, our work calculations will be the same. Me and a tractor. Now, between me and the vehicle, who do you think is going to have an easier time doing this task? The vehicle. But as long as I'm pulling with the same force for the same distance, this formula does not see a difference between us. According to this formula, I am as impressive as the tractor, which is not true. And that is where power comes in. Power, that line does not need to be there. Power is work over time. It tells you how quickly the task is performed, which is a better representation of, the strength of whatever is doing the work. Strength not only means higher power out, higher, literal force output, it also means you can do a task quicker. A stronger person would be able to get a heavy object upstairs faster than I could. So power is the rate at which work is performed. So the formula is power equals work over time. To go back to the tractor example again, tractor and I will do the same amount of work if we're exerting the same force over the distance of the field. However, the tractor's probably going to do it faster. So you divide by a smaller amount of time, and the tractor would have a bigger power output. Because a smaller number in the denominator means a bigger answer. So, two things that can do the same amount of work, but in different amounts of time will have different power ratings. Now power is a new variable, so I will point out that it is measured in units of watts. So the variable is capital P. It's the only capital P we will use in this class. And the unit is watts, which is also a capital W, because physics ran out of letters a long time ago. You've probably heard watts before, maybe as an electricity term, but its use in electricity is actually the same use here as it happens. Because when you are told like the wattage of a light bulb, like a 30 watt or a 60 watt, that is the bulb's power rating. That tells you how much energy it needs every second to stay on. So that's what a watt is. 1 watt is 1 joule used up every second. 1 joule of work done every second. Another unit for power is quite literally horsepower. The conversion there is about 750 watts to 1 horsepower. Bless you. So, power is a new variable. It's measured in watts. If the W is next to a number, it is a unit, and that makes it watts. If the W is in a formula, that makes it work. I appreciate that can still be confusing. We will practice that until it makes sense, I promise. So power is the rate at which work is performed. You could also think of it as the speed at which work is done. So why does that still say P? That's supposed to be parallel. Power has a second formula, force times velocity. If you are pulling something at and moving at a speed, you can, as an alternative formula, multiply those two things together to find your current power output. Yes?
So what are the 2 lines parallel? What is that?
It means that the force has to be in the same axis as the velocity. So, in the case of, I'm not an artist, so poorly drawn vehicle, pulling something. The vehicle is exerting a force forward, and the velocity points forward. If the vehicle was pulling forward and the box was not moving forward, it's not doing any work, it's not accomplishing anything. And secretly, these two formulas are the same, if I'm being honest. One is derived by the other. And I'm just going to prove that real quick. Work is force times displacement. Power is work over time. Whoops, why did I write T? And displacement over time is velocity. So these two formulas are secretly the same thing. Someone just rewrote it so that it might be more useful depending on what pieces of information you have. So this is on your formula sheet. I wanted to point it out. And that means you could use this to figure out how powerful your own car is, if you know its pulling force and how fast it can do that at. It also means, any athletes in the room, you can use this to figure out how powerful you are if you're able to pull something heavy while running. When I taught high school labs, I would use this to let my students figure out how powerful they were by running up a flight of stairs, but we have neither the time nor a good staircase, unfortunately. Questions about the formulas for right now? All right. Just to kind of show their use very quickly. I'm going to demonstrate here that these two people in this example will do different amounts of work in different amounts of time, and will as a result have different power outputs. Person 1 is carrying a 100 Newton box up a flight of 30 meters stairs. Point one, it's gonna be force times displacement. So person one does 30,000 joules of work in 1 minute. So their power output will be 30,000 over 60 seconds. So their power output is 500 watts. The second person is carrying a lighter box up the same flight of stairs. So they are only going to do half as much work because the box weighed half as much. But they did it faster. They did less work in less time. Specifically half as much time. So we're going to take that half as big work output, divide it by half as much time, and get the same wattage. So despite the fact that person one did more work, these two people have the same power output. Power is not only a function of strength, it is also a function of speed. So if you can do something quickly, that's often as good as raw force output, if not better. Now, that's the last new piece of information before the test. We will spend Friday reviewing everything and looking over the practice test before next week. How do you guys feel? All right. That's the end of lecture day. We'll take a brain break and let me know if you need anything, and see you Friday.
Do you have office hours
Online.
on Thursday?
Yes.
And then today, you said that.
12:30 to 1:30, and then from end of lab till 5.